And I'm going to go over to
I
Canvas.
actually I actually have a quick question just on the testing schedule. So will lab Monday lab take the test on Monday and then Wednesday lab will take the test on Wednesday?
Yes, you can switch though. It doesn't matter. I just have to split the class up because it's too big for everyone to fit in one day. So does that answer your question?
Yes, thank you.
Sure. What happened to Canvas? Let's see, let me do one thing here real quick. Where's Canvas? There's Canvas. Okay, so the dry labs for Unit 1 are in Canvas files, lab related. So if you go down to here where it says Unit 1 Dry Labs, that's the worksheets. There are it goes through alcohols. I'm going to cover alcohols on Monday. Then we'll have a review on Wednesday. Then following week we'll have our first test. Okay, so it's basically this was done by a colleague of mine, and I modified it a fair amount, but it's basically a collaborative effort. Now, this is a flow chart I put together
We
to
can
help
see.
you with your reactions. Now, you should print this off. Well, if you print off Unit 1 reactions, you're going to print it off anyway, but you'll be have access to this on the test, but it's a generic flow chart of where we want to go. I'm going to be using that today. Here's kind of a preview of what the dry lab looks like. Um,
Excuse me?
yeah,
We can't see, I don't think we could see your screen. It just says that Thomas Ferguson has started screen sharing.
okay. Let me stop screen sharing and restart it. You guys see it now?
Yes.
Yep.
Okay, let me go back up the top then. Okay, so this is the flow chart I put together. Actually, probably going on about 18 years now. That's how many years I've been teaching 306 or a variant of 306. But anyway, it's a really nice flow chart. It uh, kind of lets you know when we get into the synthesizing, how do you make stuff? For example, if we're going to make an alkene, how do we make it? Well, we can make it from an alkane. We can make it from an alcohol. Um, there's alkene down here. So, and then you just put in the structure. You replace the block here with the structure. And I'll be demonstrating that today quite a bit. But anyway, print this off and just refer to it whenever you do reactions, unless you've memorized it, but I'd suggest printing it off anyway. Okay. Okay, are there any questions about this? It looks a little um, grainy to me in terms of lots of things are on it. It's very busy, but once we start taking it apart, then you'll find this very, very useful. Um, some teachers have you memorize basically this. And I'm not big on memorization when you have a nice tool available. Um, okay, all right. So this is what if you haven't printed it off yet, this is what it looks like. We're doing naming. Every test is going to have three parts. Naming, going from the name to structure, structure to the name, reactions, and intermolecular forces. So here's some structures you'll be naming, naming structures, kind of getting uh, more confidence in building line structures versus condensed structure formulas versus molecular formulas. So we're not going to be doing too much of this condensed structure formula. Well, I can't draw on this screen. How nice. We're going to mainly be doing the line structures like this. So not too much of this. Okay, so here's more naming. Okay, here are the reactions. And we're going to be talking about these reactions, actually, all of these today in a little while. But anyway, it's quite a few pages, but and it's also worth 2 labs, not 1 lab. Okay, so anyway, that's where it's located. Are there any questions about how to find it on Canvas? So we're not doing Unit 1 dry labs in your lab packet. We're doing this one instead. So your first lab packet experience is going to be on alcohols, and it's lab number titled alcohols. Okay, so let's stop this share. And yes, there's a study guide for the exam. I think it is on Canvas, actually. This is the test, by the way, I gave to last semester, spring. Let me see if there is a study guide here. Okay, so I'll put one up. I'm going to make myself a note. Could someone send me an email to remind me? And I'll make myself a note also, because that's really important. Okay, so let's zoom over to the actual lecture here. Okay, and remember all these slides are available on Canvas. If you go to Files, Unit 1, you'll see Slides. And then you can print these off, which I highly recommend. And then you take notes from the lecture directly onto the slides. Okay, so last time we talked about saturated hydrocarbons. Those are the alkanes. And there's 2 types of unsaturated hydrocarbons. Actually, there are 3 types. We're only going to be studying 2 types. In fact, the next slide. So we're not talking about alkynes, which is unsaturated. That's a triple bonded carbon or nitrogen. Those are not in the body naturally. And since this is an allied health class, we're not going to be covering triple bond reactions. You're going to have plenty of reactions, trust me. But anyway, we're not covering those. Also, we're going to be doing organic polymers only, not plastics. Okay, so the 2 types we're going to be talking about are alkenes and the aromatics. Now, aromatics we talked about last time. We're going to talk about them in more detail today. And alkenes are double bonded. So, unsaturated hydrocarbons are a combination of single double bonded carbons. Now, the thing about double bonds versus single bonds, single bonds are more stable than double bonds. Hence, double bonded compounds are more unstable than single bonds. So the saturated hydrocarbons are more stable than the unsaturated ones. That's why unsaturated fatty acids, like linoleic acid, corn coming from corn mainly, is prone to polymerize and become oxidized. And there's some danger in that also. And I'll talk briefly about that. So it's important to, and those are generally classed as seed oils. So if you can avoid seed oils like corn oils, vegetable oils, canola oils, try to, if you can, because they oxidize more easily, and the oxidized products are not at all good for you. Okay, a point of clarification on naming. When we're naming stuff, remember we talked about the mono, di, tri, tetra, etc. To ignore those. Those will not come in the alphabetizing, except for iso, like isopropyl. So isopropyl begins with an I. Dipropyl is a P. So this is an I, this is a P. In terms of alphabetizing, when you're putting your branches off the carbon backbone in order. Okay, so let's talk about naming here. Like we did last time, first thing you're going to do is you are going to find the carbon backbone. Now, in this case, in fact, let me erase the notes from last time. Okay. So step one is to identify the carbon backbone. So to do that, that is, again, is the longest chain that includes the functional group. Now, the functional group with alkenes is the double bond. So here we have a 4-carbon alkene, butene. Okay, so here's the carbon backbone. And there are no carbons off the carbon backbone, so there are no branches. And the functional group is alkene. So this is going to be the functional group's name. So we've got, remember, there are always 3 parts to naming. This part's optional if there are no branches. Okay, in this case, there are no branches. So we are going to not worry about that. Okay, so this is the backbone here. And then this is the functional group. Okay, so in this case, we have a 4 backbone, which is a buta. And the functional group is a alkene. Now we have to say what carbon on the backbone is the functional group. Okay, in this case, it's going to be carbon number 2, regardless of which way. So if we numbered from left to right, it'd be 1, 2, 3, 4. If we started on the right, it would be 1, 2, 3, 4, going from right to left. Now, notice the carbon that if we're going from left to right, the carbon that the double bond starts on, I'm going to repeat, starts on is carbon number 2. If we're going from right to left, the carbon double bond starts on carbon number 2 also. So it doesn't matter which way you name it, it ends up being the same in this case. So it's going to be 2-butene. Okay, now the difference in double bonds as opposed to all the other functional groups, double bonds take up 2 carbons. All the other functional groups take up 1 carbon off the backbone. So basically it's as you're going into the double bond, what carbon starts that double bond, not ends it, but starts it. Okay, is that clear? Now, I'm assuming by your absence, everyone agrees. All right.
Yeah, makes sense.
Okay, so let's do another one here. In fact, let's throw in a branch. Let's throw in, let's see, let's draw this for the line structure here. Okay, and then on carbon number 2, it's going to be the double bond. Okay, so let's identify the carbon backbone. Now you can do this in one or two ways. Do the carbon backbone first or the functional group first. I have been all my years, I usually do the backbone first, but you can do it either way. You only have to put the same place. So this is the backbone. And since the double bond is skewed to the right, that's going to be the lowest number, but you can do it, you can number it both ways. Okay, so we've got I had to lift my marker to get this last little branch there. So that's officially a branch. So here's the backbone again. And so it's going to be numbered 1, 2, 3, 4, 5, 6. Okay, so it's a 6 carbon backbone. With a methyl branch on carbon number 5. So, so this is going to be hexene. Now, normally we go with everything except alkenes, we go hexa. There's an A here, but not with alkenes. We leave that A off. Okay, because it would be a hexane. If we put the A there, and no one pronounces the A, so they've over the years just eliminated the A. All right, so we have a hexene, and where's the double bond start? What carbon? Carbon number 2. So it's going to be 2-hexene, and we have the branch on carbon number 5. Now, you don't restart naming with the branches. The functional group determines the order, not the branching. Now, when we're talking about alkanes, because there is no functional group with alkanes, because it's an H, then we have to look at different numbering to see which gives us the lowest number. That all ends when we get away from alkanes, however. So let me repeat again, the functional group determines the order, the carbon numbering, not branching. Branching comes last. Okay, so you either start here or start here, either one, then this goes last. So we're going to go 1, 2, 3 steps. Or you can do 1, 2, 3. Okay, so does this make sense, this naming with the double bonds?
Yes.
Thank you for responding. Okay, so let's look at these two here. This is very similar to what we just did. This one here. 1, 2, 3, 4. 1, 2, 3, 4. And we've got a branch on this guy here. Okay, so when I sit at my computer, I share the bench that my piano is at. So I have to constantly be moving my piano bench around, which I'm doing right now. Okay, so let's identify the carbon backbone. Okay, it's 4 carbons long. Functional group is going to be a double bond. Okay, so since the double bond is on the left side, that's going to be the lowest numbering. So we're going to go 1, 2, 3, 4. So branch on carbon number 3, and it's a methyl. Okay, so it's going to be a butene, 4 carbons, and a double bond. And a methyl group on carbon number 3. Now, what have I left off?
You left off the number that the first double bond starts at.
Yeah, I didn't identify what carbon the functional group is on. So on all molecules except for alkanes, we have to say what carbon the functional group is on. In this case, it's carbon number 1. Okay, now I want to characterize something here between these two. Let's do 2 butenes. We have this one here. And then we have this one. Okay. Now they're both 4 carbons long. 4 carbon backbone. And right. Okay. So let's look at this here area. This has got 2 H's here. This has got an H and a carbon. And this has got 2 carbons. So this complicates naming, because if we looked at this, this is going to be a butene. In fact, let's simplify this a little bit. Let's not have a branch there. Okay, so both of these are a butene. However, if I started with 2 butene, there are 2 molecules that can be drawn from 2 butene. This is what they look like. So we have a hydrogen, carbon, for that carbon, your number 2. Carbon number 3 can have, there is a H here too. Now we can flip this. If we look at this mirror image of this. So we're concentrating on carbon number 2, carbon number 3. Okay, so let's look at this down here. Okay, here we've got and there's no way to redraw that like we did up here. Notice up here on this first example, let me draw my carbon backbone in. Notice that the carbons are going a different direction on this first one here. Notice how carbon goes up here, down here. Over here we have carbon going down, carbon going down. So we have an isomer, 2-butene and 2-butene. How do we distinguish the difference? Now, remember we talked about alkanes. We talked about alkanes in general are not rigid, except cyclic ones. Cyclic ones are rigid. That means all the carbons and everything cannot move around because single bonds can rotate freely about the single bond. Double bonds are all rigid about the double bond. So we have to distinguish whenever we have an alkene whether there is a isomer. So down here, if these H's are equivalent. So this is always the same way to draw it. So there's no isomer here. Because when you look at, there's a hydrogen here. There's no 2 ways we can draw this because these hydrogens are identical. Up here, what comes off the double bond? We have a carbon going one way and an H going the other way. They're not the same. So we can draw it like this is the alternate versus that. Now, how do you distinguish between the 2 in the naming? Okay, when the carbons are on the same side versus opposite sides. If it's opposite sides, that's called a trans. So this would be called trans 2-butene. And this would be called cis 2-butene. Now you've heard a lot about trans fats. This is where this comes in. Okay, natural fats are cis, not trans. So if we're eating foods that have been modified with modifying the fat in membranes are made up of fatty acids, and we're making them up with trans fats, that membrane is not going to be as secure as one made up with cis fats. Okay, very interesting chats I need to address here. Let's see. Okay, can you explain again how to get the methyl and butene? Hunter, is this more clear now from when you asked the question?
No, I wonder, how do you name it like 3-methyl 1-butene from looking at the picture?
Well, you have to find the backbone.
Mm-hmm.
In this case, the backbone's in yellow, first step. Next step is you have to number the backbone. I didn't number it here, but I did number it over here. Okay, so like this example up here, this is the methyl here. And what carbon number is it attached to?
Oh, 5.
5, so that appears there.
Okay.
And with the double bond, the hexene, what carbon number does it start on? Carbon number 2, that appears there.
Oh, the hexene is like the double bond?
Yeah, the ene is a double bond.
Okay, yeah.
Hex is how long the carbon is. So
Oh, got you.
this is the functional group. This is the backbone length. And this is the branch.
So by the backbone length, you count the lines or
You count
oh, never mind. Hex is 6. Never mind. I got you.
But okay, so whenever we do a line drawing, the beginning is a carbon, the end is a carbon, and every kink is a carbon. So we've got
Mm-hmm.
beginning, end, 1, 2, 3 kinks. So that's how many excuse me, we have 1, 2,
6, 7.
4. Yeah. A beginning and an end is 2, and then 4 kinks. That's 6 altogether.
Right.
Better?
Yeah.
Cool. Thanks for asking that question.
All right.
Half the class is probably wondering the same thing.
Yeah, I actually had I think that actually clarifies something for me. So just to clarify, double bonds end with ENE and single bonds end with ANE.
Exactly.
Okay, perfect. Thank you.
And the ANE, I call it a functional group, but most people don't. Because when you get into naming alkanes, there is no functional group that's different than any of the other bonds. So really then, excuse me, then you just look at the branching, which determines the numbering. As soon as we leave alkanes, get into everything else, the functional group specifies where the numbering starts and ends. And then the branches hang wherever. Okay, so I want you to take a note on this. So this is a red flag. Rigid structures, check for isomers. Okay, double bond is rigid. Check for isomers. Now we're going to find this is true throughout, let's see, it'll be true for unit 1, 2, 3, and 4, not 5. 5 is when we get into pure biochemistry, and there's a lot of cis trans in there, but they don't, we're not doing reactions, classic reactions like organic chemistry, biochemical reactions, it's a little different. Okay, so rigidity means check for isomers. Okay, so we have a double bond down here. Are there isomers? Well, if we change the H's, it's the same molecule. So there's no isomers. So whenever you have a double bond on the end, So because of this, whenever you have a double bond on the end, there are no isomers. Because the H's are equivalent. Now, if we had a different H, like we had an H with a proton, that would be called deuterium. Not, excuse me, we had a neutron in there. Or we could have two neutrons, that'd be tritium. So if these H's are equivalent, nothing weird or exotic about them, then there's no isomers. Okay? All right, well, let's go on here. Okay, let's see here. Now, you can have two things here. Let's- By the way, Denise, are you there?
Yes, I'm still here.
Good, so it works.
Yes, thank you. Sorry
Sorry
for
about-
earlier.
Sorry about not giving you the Zoom. I should have thought.
You're totally fine. I get it.
You have it now, and it's the same for Monday and Wednesday. There's no news. There's no new ID. It's repetitive.
Perfect. Thank you so much.
Sure. Okay, so you can have single only double bonds. You can also have multiple double bonds, both cyclic and non-cyclic. Okay, and it's the same naming, except for you have to say a couple things that are different. One is you have to identify, there are two of them. And whenever you have a die, you have to have a number that corresponds to each one. So if it's a die, you have to have two numbers. Corresponding to the location of each double bond. Okay, so and notice the double bonds here appear at the end, so not to worry about isomers. Okay, so let's redraw this with a line drawing. So it's a 1, 2, 3, 4. With a branch here and a branch there. And we've got a double bond here and here. Okay, first thing is identify the backbone. Okay, so it's 1, 2, 3, 4. So it's going to be a and double bonds, and there are two double bonds, so we're going to go diene. And because we've separated the A from the E, we don't have to worry about dropping the A. Or this could be a triene as well. Now, because we have two double bonds, we have to figure out what carbons those are located on the backbone. So since this is a symmetrical molecule, it doesn't matter which way we name it, left to right, right to left. Okay, so it's going to start on 1. If we start on the right, going to the left. And 3. So it's going to be a 1,3-butadiene, and we have two branches. One branch is on 2, the other's on 3. So it's 2,3-dimethyl 1,3-butadiene. Kind of a mouthful, huh? And now, let me give you an example of how wild this can get. if you are into omega-3 fatty acids and you are buying them, for example, I buy krill tablets for their omega-3 fatty acid content. And usually if you look on the package or the bottle, it'll say EPA, so many milligrams. That's an E, not a C. And H. So this is penta double bonds. So EPA has 5 double bonds. DHA has 6 double bonds. So this is named icosa pentaenoic acid. This is, and don't worry about naming it. We'll get to that when we get to fatty acids, which is unit 3. This is docosa hexaenoic acid. So natural molecules have a ton of double bonds, a ton. And these are all and there are 5 of these. So you go cis, 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 EPA. Now EPA is defined with 5 cis double bonds, and this is 6 cis's here. So you have cis, 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 cis. And they're usually separated by commas all out here. And notice no trans. Now you can also have cyclic molecules with a double bond in them. And here it's going to be, in fact, let's do one with 1 single bond. Let's see. Okay, so we've got a 6-sided hexene, 6 carbons. Okay, so whenever we have a cyclic molecule, the functional group automatically determines what's carbon 1. So that means that is carbon number 1 here or carbon number 1 here. Which is it? Gotta count. So we're gonna go 1. If let's do this one first. 1, 2, 3, 4, 5, 6. If we do this one, and when we count, excuse me, let me redo this here. When you count, you go into the double bond, which I didn't do before, okay? So if we start on this left-hand carbon here, we're gonna go into the double bond. So that's carbon number 2 here. So in this one here, we're gonna go into the double bond. Okay, so the double bond is on carbon 1 on both of these. Problem is, which is the numbering we're going to be using? Okay, in this one, we're going to be doing and it's going to be 1 cyclohexene. If you don't put the 1 down, it's assumed it's on carbon 1. But for consistency, let's add 1 cyclohexene. And the branch is on carbon 3, so it's going to be 3 methyl 1 cyclohexene. This one is going to be branches on carbon 6, so it's going to be 6 methyl 1 cyclohexene. So intuitively, which do you think is right? Left or right? Now with the theme
Left.
left.
Yeah, I'm also left.
Yeah. With the theme, we've been going with which numbers end up being lower. And that's what the kind of the philosophy you use to name or figure out which one is more correct. So yes, this one is the correct one because of the numbering of the branch. Now, in this case, the location of the branch determines which is correct, because it doesn't matter how we number this, the double bond is always at carbon number 1. So then it becomes, where is the branch located? So this would be the backbone, both of these. And we've got a branch on carbon over here. Okay, so the double bond is not on an end, so there could be a possibility of isomers. So so let's home in on this here. So right here is a hydrogen, and right here is a hydrogen. Now, remember with double bonds, we have one less hydrogen on either side, because the carbon has 4 bonds from our Lewis structures. And if we count now, we go for this carbon here, 1, 2, 3, 4. So normally you'd have 2 H's there. For example, here there are 2 H's because this carbon here has got 1, 2, 3, 4. Except by the double bond, because one of the bonds is taken up with the extra bond from the double bond. So can we draw this any way that's different? No, you can't. Because of the cyclic nature, you're forced to draw it this way. So because of that, there are no isomers. Now, let's do another example here. Let's do this. Okay, so backbone, 6-membered ring, cyclic. So that's a cyclohexane. And we determined the naming is we're going to start with this being carbon number 1. So we've got 2 branches now. Okay, you can also name it starting over here. In fact, let me do that in a different color. Okay, so let's name the red numbering system here. So that means we're going to have 2 methyl branches. So it's going to be it's going to be 2 branches, 2 methyl branches. So it's going to be 5 and 6. Dimethyl 1 cyclohexene. If we're doing it in blue, it's going to be 3, 4. Dimethyl 1 cyclohexene. Okay, so using the same argument we did before, these numbers are bigger. So same process, the same naming philosophy would come into effect where you have the lower numbers. Okay. Okay, so we talked about this already. No free, oops, no free rotation. Hence, we have to look at, if we put the, in this case, the methyl group on the, going the other way, is it a different molecule? And it is. Okay. The physical properties of cis-trans are very close, but not the same. The trans, notice, has a lower melting point than the cis. Is that right? Which is lower, cis or trans? Well, those negative one are kind of weird. Let's look at the boiling points. Which is lower, cis or trans?
No one's trans.
Trans. Now, as far as, remember, with intermolecular forces, we have melting. Intermolecular forces, we have boiling point, melting point, and surface tension. Okay. When IMF goes up, so with IMF now, it's directly proportional to boiling point, melting point, and surface tension. So, cis, because the boiling point's higher, has a higher MF. IMF. It's supposed to be an F, not a P. And the reason for that is the trans can lay closer together than the cis. Cis kind of bump into each other. Okay. Physical properties are just like the alkanes. No difference at all. They're nonpolar, meaning they have low IMF compared to ionic now. Remember, this is compared to inorganic. So nonpolar, inorganic, or polar because they're usually ionic. They're soluble in water because they're ionic. Like dissolves like, so soluble because they're non-polar and non-polar solvents. For example, alkenes will dissolve nicely in gasoline, but not in water. They are usually, not always, but most of the time, they're less dense in water, meaning they'll float. Okay, and then inorganic stuff will sink. And these are soluble in polar solvents, think water. Okay, as the alkenes get bigger, their boiling point goes up, their melting point goes up, and their density goes up, and also surface tension goes up. Okay. So let's. Okay. So our first alkene reaction, and before I go into the alkene reactions, I want to talk about, there were two reactions that I didn't talk about last week on alkanes. So if we look at our flow chart, alkanes have two reactions. They'll react with chlorine gas, and under heat or UV conditions, you'll end up with a halogenated alkane, or they'll burn. Those are the two reactions. They're pretty simple. Alkenes, though, have this is one reaction, two reactions, three reactions, four reactions, five reactions. So now we have a total of 7 reactions, and really 8 because they also will burn. We have 8 reactions now. Went from 2 to 8 now. And we haven't talked about alcohols either. These are just the first 2 chapters. Okay, so the first non-alkane reaction I'm going to talk about is, oh, by the way, this reaction is called a substitution reaction. So we're basically substituting, for one of the hydrogens here, we're substituting a chlorine. This one, this series, is we actually are adding to the double bond. Okay, and it is called, oops, this is, yeah. Here we're adding to the double bonds, hence they're called addition reactions. Okay, so we have the double bond, whatever is attached to it over here. Usually you do things like R, 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 and those are just something. In other words, this doesn't exist. These could be H's, they could be other carbons, it could be other nitrogens, whatever, something. We're going to add this AB across that double bond. Now, there are 2 ways or 2 types of additions we have. We have homogeneous additions, and we have heterogeneous additions. Homo means the 2 atoms are the same. Hetero means they're different. And you end up with different products. Secondly, those double bonds, we have, now remember, a bond is composed of 2 electrons. So we have an electron here, electron here, electron here, electron here. However, these 2 bonds are not equal. The name of one of the bonds is called sigma, and the other is pi. So we have a pi bond and a sigma bond. Okay, so pi bonds are very stable. pi bonds are not stable. So when we react a double bond with something, guess which one stays, the sigma or the pi bond? Because you end up with a carbon single bond. Which is more stable? Sigma. So whenever we react a double bond, the pi bond goes away. Because of that. So the pi bond goes away. Leaves us with sigma. And that's a stability thing again. Okay, so we have a double bond, single bond. And this is the sigma bond. Okay. So let's look at the first group, which is going to be the simpler one, is the homogeneous additions, which are going to be these guys here. This is too busy here. Okay. I'm not going to be using bromine much at all. 99% of the time, we're going to be talking about chlorine. Biochemically, whenever they modify things, most of the time it's with chlorine, not bromine or fluorine. Okay, so let's talk about this one first. So this is be the homo. Hetero. I think that's spelled right. Doesn't look right though. Anyway, same, different. Okay, so let's. Okay, so here we have a addition reaction, number one, because we're going to add something to the double bond. Number two, it's a homogeneous add-in. Not a hetero. Homos are simpler than the heteros. Okay, so what happens is the BR, let's call this BR1, BR2. So the BR1 is going to add to one side of the double bond. The BR2 is going to add to the other side. So we're going to end up with, it's going to be like that. Now, if it's a homogeneous addition, you can't distinguish between the BRs. They're different physically, but they look the same. So the important thing here is, and you'll get to it in a second here, there's no mixture. And that's what makes these simpler than the heterogeneous additions. So this is where we are right here. You go from the alkene, adding a, in this case, bromine, which I said we never use, but anyway. And we end up with a haloalkane, no mixture. Okay, so let's do an example. Let's do the example with So whenever you do reactions, you've got a name. This is the reactant side. And here's the product side over here. Reaction is what you start with. Products is what you end with. And let's add chlorine gas. Now you have to look at, this will tell you if there are any conditions. Like here, the conditions are water and sulfuric acid. Here, there's sulfuric acid and heat, etc. Okay, well, whenever we add a homogeneic addition to a double bond, there's no mixture and no conditions. You just add it. Let's see, we're down here. Okay. Now, whenever we think of homogeneous additions, I want you to think instead of Cl2, we're going to use it as ClCl, like that. Same thing. This will make more sense. And what happens then, the chlorines will add across here. So we're going to end up with okay, so we have to name these now. Products and reactants. So the reactant side, we're talking about 1-propene. Okay. 3-carbon backbone. 3-carbon. Functional group is ene. And there are no branches. Okay, over here, on the reactant side, we've actually on the product side, we still got a 3-carbon backbone. Now, most of the time, the backbone stays the same. 3 carbons, 3 carbons. Start with 3 carbons, ends with 3 carbons. Sometimes you add, though, backbones. So you'll have a primary backbone and a secondary backbone. We'll get to that later. For right now, you start with 3, end with 3 carbons. Okay, so we need to name this. So it's going to be a propane with 2 chlorine branches. So it's going to be dichloro. That's going to be positions 1 and 2, propane. So 1,2-dichloropropane. Now, when I said there's no mixture, so that's all we get. The 1,2-dichloropropane. Okay, so this is your first real reaction. So, 1, you have to list conditions, and there's no conditions added to the chlorine gas. You know, like heat or acid or metal cal, whatever. Nothing. It's just plain old. And the reason for that is this double bond is so unstable that it doesn't need anything to juice it up. It goes right away. Boom. You add chlorine gas to any alkene, it'll happen. Okay. So is this clear? And one last thing is this is stable, non-stable, relative to what we're trying to make. And the reason why this happens is because the product is more stable than the reactant. The product is more stable than the reactants, why the reaction goes. Now, all reactions, almost without exception, all reactions, it's not a one-way trip. So what happens during the reaction, sometimes the products are reconverted back to the reactants. So you get this ratio of product to reactants at the end. Now, the more stable the product is compared to the reactant, you'll get more product than reactant. Sometimes you get very little reactant back. It's called a complete reaction. And there's a ratio between the product and reactant. It's called equilibrium constant, which you might have covered in 305. Did you cover equilibrium in 305?
Sorry, one more time.
Did you cover equilibrium in 305 or equilibrium
Yeah.
constants? Okay. Where you have product, the ratio is product over reactants. That's correct.
Yes.
Yeah, you do.
Okay, good. Okay, so then in the case of this, you'd have a much more positive equilibrium constant because you have more product than reactants. Okay, and the reason why this is more unstable is the pi bond of the double bond is gone, only sigma's left. So this would be sigma, sigma, and this would be sigma pi, and this would be sigma. So the pi goes away. And the electrons that are in the pi bond with the two chlorines, one each chlorine. Okay, so that's your first reaction. Now, a typical test question is I might say, how do you make this 1,2-dichloropropane? What do you start with? Or I might say, here's one propene and I added chlorine. What does that end up making? Those are the two types of reactions questions. There's a third one too, which is a multi-step reaction. And we'll cover that at the very, very end. In fact, we're going on an hour, 15 minutes, and we're okay. All right. So are there any questions about this reaction? We're gonna be doing lots and lots of reaction examples. Okay. Now, one of the homogeneous addition you can have is with HH, or hydrogen gas. This is called hydrogenation. And this here is a big deal. It used to be more important than it is now because the whole food industry relied upon Crisco, vegetable fat. Now, back in the 50s, my mother thought, as did probably 95% of the country at the time, that lard was very unhealthy to consume. And so the food industry wanted to have a substitute that's quote unquote healthier than lard. So my mother and most housewives, cooking housewives in the country, thought that was a good idea too. That made sense to them. So what are your alternatives? Well, take that. So what are your alternatives? Well, the food industry decided to take vegetable oils that are liquid, like corn oil, canola oil, and make them more lard-like, which are solid at room temperature. And my mother used to bake a lot. She used to make her pie crust from scratch and her pasta from scratch and all this stuff. She used Crisco. Now, the reason for that is the lobbying industry at the time in the vegetable oil industry was stronger than the lobbying for the swine industry, pigs. And that's why that happened. Now, what happens is they take a polyunsaturated vegetable oil and hydrogenate it. Saturated oils are solid at room temperature. Unsaturated oils at room temperature are liquids. Now, when we make soap, we're going to do the same thing. Either start with a liquid fat or a solid fat, and you'll get different kinds of soap. Okay, so this is the deal. And when they found out that trans fats, because when this happens, well, when this happens, the bonds are converted to single bonds, but not all of them. The double bonds that are left over, not 100% reaction, are converted from cis to trans. And so that's how a lot of trans fat got introduced into the Americans, well, internationally, diet, which I'm a product of. My mother used to cook a lot. She was Miss Betty Crocker. I don't know if she loved to cook, but she cooked a lot. And my dad was from the South, so he liked lots of bacon grease in his food. My mother's from New England, and she was very Italian, and she cooked with lots of different things. So she could adapt. She adapted very easily to some of the needs. So anyway, bottom line is, the reason why I brought that up is Crisco faced obliteration when they found out trans were bad. So what they did is they reformulated their fat, their vegetable fat, and they ended up, instead of hydrogenating a vegetable oil, they ended up by mixing saturated fat oils to get their consistency they wanted, which ends up being much healthier. Okay, sorry for that little tidbit, but hydrogenation used to go on big time, and it's because of that trans conversion of the unreacted double bonds on the fats, converting over from cis to trans. That's what stopped everything in their tracks. Interesting. Okay, so when you add hydrogen to a double bond, okay, it's an addition reaction. It's a homogeneous reaction addition because the H's are the same. So we add an H to each carbon, we end up with an alkane. However, in this case, the double bond is not compared to the alkane, is not as unstable as before. So you've got to add a catalyst to make it happen. It won't happen just by bubbling hydrogen gas through an alkene. So that is in our flow chart. Right here. Notice the direction of the arrow. So the direction of the arrows is the head of the arrow is a product. The tail of the arrow is the reactants. Now notice we can take an alkane and oxidize it, and it'll become an alkene. Now this is done biochemically all the time. For example, in the citric acid cycle, it's done a lot. And we'll get into that in Unit 5. Okay, and there's no mix because it's a homogeneous addition. So we have two homogeneous additions, a halogen gas and hydrogen gas. And we have no mixture. So if we took butane and added H2 hydrogen gas with a metal, frequently platinum, that's uppercase platinum, we're going to end up by putting hydrogens on either side of that carbon there. Backbone remains the same. So this is going to be plain old butane. Okay, so that's the simplest addition reactions. We're adding a homogeneic addition to the double bond. Okay, so we have reactants, products, and we've named them. And there is no mixture. Now, what you're going to see in a minute here, I'm going to do one more reaction before we're done here. And then we'll pick the rest of this up on Monday. When we have a mix, we have to determine which is more stable of the mix. Okay, so before we get into all that, do you guys have any questions about addition reactions using homogeneic additions? Now, your dry lab, you can be practicing this kind of stuff. Okay. So in organic chemistry, symmetry and this Markovnikov rule comes into play when we're determining stability. So what do I mean by symmetry? Nature likes symmetry. Even though it's not spelled right. Symmetry. And this is TRY. Okay, and then they also have something called the Markovnikov rule. Both of these determine how stable your products are. And this is of a product. Okay, so symmetry is just you eyeball it. Which looks more symmetrical? Which looks more symmetrical? Left or right? Left or right?
The one on the right?
Right.
Exactly. The one on the left is all kind of lopsided. So I put symmetrical with a checky mark. Symmetry over here is not. So if we had these as products, we would choose the symmetrical one. However, there's another factor that comes into play. And this is this Markovnikov's rule. So basically, when we look at a molecule, we go to the ends of the backbone and the ends of the branch. So this is our backbone. We're going to go to the end and we count the hydrogens. This is 2, that's 3. So let's apply that rule here. So we're going to have mark. This is an A. And mark. Okay, so let's count the terminal hydrogens. Either 2 here, 3 here. We have 3 here, 3 here. So let's count them. On the left, the 1 butene. How many hydrogens do we have total? For those that have taken pre-calc math, 2 plus 3 is 5. 3 plus 3 is 6. Which is more, 5 or 6? Okay, so this is another reason why the right-hand butene is more stable than the left-hand one. So you always have 2 tests. Sometimes symmetry is a wash. Really can't tell. That's why we always do 2. So you have a symmetrical test and a Markovnikov test. So this, to me, complicates it. Basically, we just count the hydrogens. Ones when those hydrogens are more stable. And those are usually the more symmetrical ones. I don't know, same thing there. And, it varies on whether it is, but basically, the symmetrical ones are more than or the more stable ones are more than the less stable ones, always. Okay, so when we look at our flow chart, I will tell you to expect a mix. For example, here. So we're creating an alcohol, we're creating a halogenated alkane. Now, when we burn alkenes, they go to a non-organic molecule, usually, carbon dioxide and water. Basically, everything on this page can be burned to carbon dioxide and water. So everything undergoes combustion. Okay, so let's see what this stuff looks like here now. All right. Now, this molecule tumbles. Okay, so it's rotating around. So when it collides with a double bond, statistically, the H can be on the left side or the H can be on the right side. Pure statistics, 50-50. Okay, so that makes sense. It's important to understand this concept. So because the molecules are in motion, the odds of hitting it a particular way are 50-50. Hence, you're going to get some products with the H on the left, sometimes the H on the right, sometimes the Cl on the left, sometimes the Cl on the right. Okay, unless this is an exception. Gosh. Also, I was writing left-handed. Okay, so the exception is this, and that's because what you end up with is this happens. The HCl hits it like that, but you end up with the same molecule. Normally, that doesn't happen only when you have a balanced alkene like that. It happens. Okay. All right, so let's take an example. Let's add hydrochloric acid to an alkene. Okay, so let's so first thing, let's name the reactants. Okay, we've got 1, 2, 3, 4, 5. So that's pentene. So we're going to end up with a 5-carbon backbone. And this is going to be 1, 2, 3, 4, 5. Okay, so because this is not balanced like this, where we have 2 carbons, 2 carbons, we're going to end up with a mixture. And most of the time, you're going to get a mixture. Okay, so here we have this carbons 1 and 2 versus carbons 3, 4, and 5. So 3, 4, and 5 side is longer than the other side. So you're going to get a mixture, not balanced. So the first time the HCl is going to add across it this way. Then the HCl is going to tumble, and 50% of the time it's going to add where the chlorine is on the left. Chlorine on the right, chlorine on the left. This is why we have a mixture. So we have to have 2 product molecules over here. It's a little smaller, so we have brown. So let's do the top one here. Let's do this. Blue. Okay, so in the case of the red, the chlorine ends up on the number 2 carbon, which this here is. And then the H ends up on the number 3 carbon. With the blue, so those are the 2 products. And it happens to be just the way the HCl's land across the double bond. Statistically, it's 50-50. However, one of these is more stable than the other one. You have to do our 2 tests. In fact, I'm gonna let's see, let's do that's more room. Okay, so we need to do the 2 tests. We have the Markovnikov and symmetry. Remember, we have to circle the one which is more stable. All right, let's do Markovnikov first. So we've got 3 H's, 3 H's. We have no branches. So that's going to be 6 hydrogens. Here we've got so it's clear what's going on. Okay, so we've got 3 hydrogens, 3 hydrogens. So they're both 6 hydrogens. So Markovnikov doesn't tell us which is more stable. Symmetry, which is more symmetrical, left or right? Has to do with the location of the chlorine. Which is more? Huh?
Left.
Do we have a left? Do we have a right? I don't see
See,
hand.
right?
Okay, so the right one, the chlorine is more central than the left one. The chlorine is a little off center on the left one. The right one, the chlorine is exactly in the middle. So symmetry, it's more symmetrical, the right one. So we'd circle this one. So that's why we have to do 2 tests, Markovnikov rule and symmetry. Because Markovnikov doesn't tell us anything. They're both terminal carbons, both has 3 hydrogens. So now we have to name them. This is going to be 2-pentene. And this is going to be, chlorine is going to be in carbon number 3. So it's going to be 3-chloro-pentane. And this is going to be 2-chloro-pentane. Now, points on a test come from reactions. You're not going to get as many points for naming stuff. You're not going to get as many points for discussing intermolecular forces. Okay, so I'm going to end on this particular one. Now, on Monday, we're going to pick up on addition reactions with some more variations. Okay, so I want all of you to print off or have available this flow chart. In fact, let's talk about this flow chart some more. Okay, flow chart has arrows in it. The arrows refer to these, these arrows. You've got conditions, and you've got additions. So we have to name everything here. So this would be or H plus, either way. And this is going to be, this is a tough one. All right. We name this, we name the reactants, and we have to name, I didn't name the products here. Anyway, we have to name the products as well. So this would be, we'll talk about that Monday, naming these alcohols. Okay, so there are arrows in the flow chart. The head of the arrow is the product, tail of the arrow is the reactants. These are the addends. And or conditions on every one of these. Okay. So we're going to talk about benzene quite a bit on Monday. And then we have one more addition reaction, which is hydration. Okay, what do you guys think of reactions?
Feeling all right
There's a-
on them? Ready for lab?
There's a lot of them.
A lot of, we're up to 8 reactions now. Jumping from last week to this week. Okay, when you're starting the second dry lab, until we talk on Monday, don't do anything with a hydroxyl group, an OH in it, because that's an alcohol. We haven't talked about alcohols yet. So just do everything else. And it's not all due together because there's a lot of here. So just it'll start with alkanes and throw in some alkenes and it'll go to alcohols. And then of course, if you want to review last semester's alcohol video, it's available under modules. Download the slides for Monday. Take some notes on the slides. Make sure you have a printout of your flow chart. Okay. Now that's kind of a harbinger of what's coming with units 1 through 4. You're all going to have naming, you're going to have reactions, and you're going to have intermolecular forces. Now, someone asked about lab today. The lab is both in person and at home. So whatever you feel comfortable. If you're driving long distances, versus wanting to do it in person, either way is fine. Wet labs there's no doing them at home. You've got to do them in lab. But dry labs are worksheets basically. And my philosophy is you can do worksheets as well at home as well as in person. You can also work in groups with dry labs. And you can be working with a group or groups also with wet labs. None of the labs you're going to be doing by yourself.
I
Okay.
had a quick question. Is the dry lab for this week the thing you showed at the beginning of the Zoom meeting?
Yeah, let me show it to you again. Yes, but I'm going to show it to you again. Okay, so we're going to go over to Canvas files, lab related. Okay, and let's do where's lab related? Go to the bottom and it'll say Unit 1 Dry Lab. That's what we're doing starting today, which is what I showed you at the beginning of the lecture.
Thank you.
Professor, I also have one question. Hello.
Yeah.
So do we have a dry lab today? Or do we have to come in person for that?
As I was explaining a few minutes ago, yes, we have a dry lab this week and next week. And dry labs, you can come in person or at home.
Okay, thank you.
Professor?
Yeah.
So for today's dry lab, how long are you guys going to be there? Because should I show up late? Or because
Yes,
last time it was kind of quick.
Yeah, the only problem today showing up late is I have to go over to security to get my parking pass. And I don't know what time they close. I think they close at 5. And it'll take me like, between the time I walk out and drive over there, 15 minutes. Probably not that long, but just like 15 minutes. So I have to leave basically at 4:30 today. So how late do you think you'll be?
It's just that the anesthesiologist had to hold up a case. So I was thinking maybe 4.
Do you have to drive very far?
Yeah, I have to drive quite some way from my job.
Then don't come.
Okay.
I mean,
Oh,
that's my opinion. You can still come if you want, but you know, I don't think you should come with your long drive.
okay. I'll just save my drive, and I know that for wet labs we have to be there on time and for the test.
Yep, exactly. But you know, we can have a private or a group Zoom session as well. Like on a Tuesday or Thursday, you guys. So you know, if you like before the tests, we're gonna have a unit 1 review the before the tests. And basically I'll go over practice tests with you from last semester, which is which would be this one here. Back, we should move this.
Professor, also, if I have any questions on the dry lab, I can just either text you or email you, correct?
Yes. Mhm. Yep. So here's a unit 1 review, practice test from, you know, I've got lots of practice tests. Now this Chem 131 is the name of the class up in Tacoma. That's the same as 306. Whenever you see 131, it's Tacoma. So yes, you can always text me or you can always send me an email because I monitor it from my phone. And if you're texting me about a specific problem, it's best to email me, take a picture of the problem or reference it, and then use Outlook to send it though. Attachments in Canvas are flaky, so use Outlook. Attachments in Outlook are very solid. So yes, yeah,
Professor, I have a question.
yeah.
I know for the first one you included answers. Are you going to post answers to all of our dry labs like once after everything is supposed to be due? So we know if we're doing it correctly?
Yes, and I'm trying to think. What I'm checking is I'll post a zipped file of the answers. I'm making it out now. So you can check them.
That'd be greatly appreciated. That was like the only thing that I didn't like about my 305 professor. She was a great professor, but when she posted homework, we had homework every week. She never actually posted the answers, even though we had to like turn everything in beforehand, which is fine. But she never posted any of the answers to make sure that we were actually doing them correctly.
Yeah, all homework related stuff, which is dry labs or practice worksheets or whatever, I always post the answers. Because you're right, you never know whether you're doing it right or wrong.
I don't mind attempting a fail, but if I keep getting them all wrong, how am I supposed to learn to get them right on the test?
Yeah, yeah. Well, the problem is if you do them wrong, then you have to unlearn what you did wrong and learn it right. So it's like double the time. And you probably don't have a lot of extra time to do that. I just
Absolutely not.
I know that's what I mean. You know, it's crazy when people are astonished when I tell them, "Oh, I'm giving you the answers to the lab worksheets." Okay, you are. Does that mean we're all going to get 100%? Well, theoretically, yes. And they look astonished. And I explained why it's important to have the answers if you're doing them right, because you don't want to waste your time. There's a lot of material in this class, and you don't have time to be wasting.
But we'll get full credit for the homework, correct? If
Yeah.
we turn it in.
Well, you got to turn it in anyway. So if it's turned in wrong, what I do is I randomly choose 10 problems and grade those. And depending how wrong it is, in fact, let me just talk a little about what I mean by that. I don't do multiple choice tests ever, 0%. The reason why I don't is because I can't give partial credit. Multiple choice or right or wrong. That's it. The way I give tests is you write it in. So I look at your setup, I look at your parts of your structure. Did you name the symmetry right? A lot of parts to it. And then give you credit for each little part. So if you get all the parts right, except for 2 parts out of, say, 8 parts, then you get partial credit. Or multiple choice, your answer is right or wrong. You need full credit or 0 credit. So when I'm looking at your answers, if they're mostly right, you'll be fine. If they're mostly wrong, you won't be fine. And what I do too is if you try, I usually give you, like say the problem's worth 10 points. I usually give you 1 point for trying. Or again, multiple choice, you get 0. So my students tend to do better when I grade like that. Now my late wife would always accuse me of spending hours upon hours upon hours grading tests. Tests are like 8 pages long because these chemical structures are big, and it just takes up more room than a math-based test. And it just, there are 40 something of you times 8. That's all, 2/3 of a ream of paper I've got to grade per test. And my wife at the time, she she said, "You'll spend all this time grading, we could be going someplace, let you some music or whatever." But anyway, I said this comes with the game. So that's my soapbox. Why I give you the answers.
Professor, I had a question.
Yeah.
So I joined the class a little bit later. So this is more clarification for the lab portion.
Is this
Um,
these?
yes, yeah. Hi. I just had some clarification for the lab portion. So for the dry lab, I'm assuming we don't need, because you mentioned that we can either do it at home or on like in person if we wanted to. I'm assuming we don't need like the safety gears and stuff. But for
Oh,
the wet lab, for the dry lab, we wouldn't need like the safety goggles and the lab coat and stuff.
yeah.
For the wet labs, we would in person because that's required to be in person,
The
correct?
only thing you need in dry lab is a lab shoe, a closed-toed shoe,
Mhm.
because you never know what's on the floor. There's no goggles, no lab coat, because the chemicals aren't out.
Right.
I mean, the chemicals are out because of 305, but they're not out for us. So
Okay, sounds good. I just wanted some clarification with that in case so I could like attend to that and purchase those items.
are you coming in today?
I cannot today. I was gonna do mine at home just because I had already made an appointment for a
Okay.
different appointment
I was gonna
part
say
of that, yeah.
you can talk some more about things that you need to get caught up on. Have you watched all the videos?
I watched a little bit right before joining this class.
Okay.
I've been taking a little bit of notes.
Well, get caught up on the videos,
Okay.
particularly the one that says alkanes and alkenes.
Mhm.
And then look at the dry lab in relation to those 2 lectures.
Okay, sounds good. I'll go ahead and do that.
And then ask me for any questions about anything. Also, there is a video on Lab Write Up,
Mhm.
because wet labs require a pre-lab to be done, and there's a
Mhm.
video on that as well. I can't think of anything else. If you have a friend in class, you can kind of discuss with them kind of thing, how things are expected.
Okay, sounds
Denise,
good.
did you join our Discord group
I
when
have
you came in?
no, not yet.
Okay. If you like, if you want, I can add you to it.
Yes, please. That'd be great. I appreciate it.
Yeah, of course.
Thank you.
Welcome.
One thing I like about teaching 306 is that students tend to be very social, and they tend to be very caring individuals. And that's one of the reasons I like to teach. See, I get to work with individuals like that. When you get into the STEM classes, they can be quite dry, real nerdy. I mean, really nerdy. And, it's just, I like to, socialize and learn about you, and you learn about me, like, I just like that. So that's why I like teaching the allied health classes. So that's why one of the reasons I like students to decorate their lab coats is because, Denise, by the way, you can decorate your lab coat for extra credit. And that can be tie dyeing, embroidery, drawing with a fabric pen, anything like that, whatever you'd like. And you'll get credit for one wet lab, 10 points. But if you do it in a group, in a study group, it builds a lot of relationship skills, number one. And number two, when you help another student, you have to understand better than if you're not helping anyone. So students in study groups achieve more than students that work by themselves. So I encourage socializing with studying or without. So anyway, as we go along, we'll talk about stuff like this. So any other questions? Okay. All right, so I need to go because I have to get to lab in time. I have great traffic, 25-minute drive. So anyway, I'll see you guys, whoever shows up in dry lab, and I'm probably going to leave 4:30-ish, so I can get over to parking, and I need to look up when parking closes too, because if it closes at 4:30, I won't be able to get over there, so I have to come tomorrow. Okay, anyway, take care, you guys. It was a good session. I hope you guys are okay when I wait for an answer. I forgot who I was talking to. They said, "Oh, he expects us to answer." That's something that's really hard to do, is to get students to be more talkative during lecture.
Do you actually want us to respond, or like, is it internally to ourselves?
Well, I'm assuming with silence you don't have a question. The thing about asking a question, though, is that other people may have the same question but are too shy to ask.
Okay.
So, I'm not marking attendance. I'm not marking whether you're answering questions or generating questions or whatever at all. This is not middle school. And some teachers tend to treat it like that. Taking attendance on every lecture, to me, is a total waste of time. If you never come to class and just look at my videos and get A's on tests, more to you. So my ego is not the fact that you come and listen to me. My ego comes into play as your achievement. If you do well in class, that's my teaching ability. In combination with encouraging you to do something called metacognition, which is your own learning process. So to enhance that metacognition and listening to me and helping you with problems and everything, that's all part of the process. So, all right, I do have to go though. So you guys, great class as always, and take care.
Thank you.
Thank you, Professor. Have a good day.
Thank you.